strut attached to it. Most turbofan engines have two spools, low pressure fan shaft, a few stages of compression and the turbine to drive it, and high pressure compressor shaft and high pressure turbine. Figure 1-70. Figure 1-70. Dual rotor turbine for split spool compressor. The remaining element to be discussed concerning turbine familiarization is the turbine casing or housing. The turbine casing encloses the turbine wheel and the nozzle vane assembly, and at the same time gives either direct or indirect support to the stator elements of the turbine section. It always has flanges provided front and rear for bolting the assembly to the combustion chamber housing and the exhaust cone assembly, respectively. A turbine casing is illustrated in Figure 1-71. Figure 1-71. Turbine casing assembly, exhaust section. The exhaust section of the gas turbine engine consists of several components. Although the components have individual purposes, they also have one common function. They must direct the flow of hot gases rearward in such a manner as to prevent turbulence and, at the same time, impart a high final or exit velocity to the gases. In performing the various functions, each of the components affects the flow of gases in different ways. The exhaust section is located directly behind the turbine section and ends when the gases are ejected at the rear in the form of a high-velocity exhaust gases. The components of the exhaust section include the exhaust cone, tailpipe, if required, and the exhaust nozzle. The exhaust cone collects the exhaust gases discharged from the turbine section, and gradually converts them into a solid flow of gases. In performing this, the velocity of the gases is decreased slightly and the pressure increased. This is due to the diverging passage between the outer duct and the inner cone. That is, the annular area between the two units increases rearward. The exhaust cone assembly consists of an outer shell or duct, an inner cone, 3 or 4 radial hollow struts or fins, and the necessary number of tie rods to aid the struts in supporting the inner cone from the outer duct. The outer shell or duct is usually made of stainless steel, and is attached to the rear flange of the turbine case. This element collects the exhaust gases and delivers them directly to the exhaust nozzle. The duct must be constructed to include such features as a predetermined number of thermocouple bosses for installing exhaust temperature thermocouples. And there must also be insertion holes for the supporting tie rods. In some cases, tie rods are not used for supporting the inner cone. If such is the case, the hollow struts provide the sole support of the inner cone, the struts being spot welded in position to the inside surface of the duct and to the inner cone, respectively. Figure 1-72. The radial struts actually have a twofold function. They not only support the inner cone in the exhaust duct, but they also perform the important function of straightening the swirling exhaust gases that would otherwise leave the turbine at an angle of approximately 45 degrees. Outer duct, inner cone struts. Figure 1-72. Exhaust collector with welded support struts. The centrally located inner cone fits rather closely against the rear face of the turbine disc, preventing turbulence of the gases as they leave the turbine wheel. The cone is supported by the radial struts. In some configurations, a small hole is 1-51 located in the exit tip of the cone. This hole allows cooling air to be circulated from the aft end of the cone, where the pressure of the gases is relatively high, into the interior of the cone, and consequently against the face of the turbine wheel. The flow of air is positive, since the air pressure at the turbine wheel is relatively low due to rotation of the wheel, thus air circulation is assured. The gases used for cooling the turbine wheel return to the main path of flow by passing through the clearance between the turbine disc and the inner cone. The exhaust cone assembly is the terminating component of the basic engine. The remaining component, the exhaust nozzle, is usually considered an airframe component. The tailpipe is usually constructed so that it is semi-flexible. On some tailpipes, a bellows arrangement is incorporated in its construction, allowing movement in installation, maintenance, and in thermal expansion. This eliminates stress and warping which would otherwise be present. The heat radiation from the exhaust cone and tailpipe could damage the airframe components surrounding these units. For this reason, some means of insulation had to be devised. There are several suitable methods of protecting the fuselage structure. Two of the most common are insulation blankets and shrouds. The insulation blanket, illustrated in figures 1-73 and 1-74, consists of several layers of aluminum foil, each separated by a layer of fiberglass or some other suitable material. Although these blankets protect the fuselage from heat radiation, they are used primarily to reduce heat loss from the exhaust system. The reduction of heat loss improves engine performance. Insulation blanket, ram air induction air cooling air ejector. Figure 1-73, exhaust system insulation blanket. There are two types of exhaust nozzle designs. The converging design for subsonic gas velocities, and the converging-diverging design for supersonic gas velocities. These exhaust nozzle designs are discussed in greater detail in Chapter 2, Induction and Exhaust Systems. The exhaust nozzle opening may be of either fixed or variable area. The fixed area type is the simpler of the two exhaust nozzles, since there are no moving parts. The outlet area of the fixed exhaust nozzle is very critical to engine performance. If the nozzle area is too large, thrust is wasted. If the area is too small, the engine could choke or stall. A variable area exhaust nozzle is used when an augmenter or afterburner is used due to the increased mass of flow. When the afterburner is activated, it must increase its open area. When the afterburner is selected, when the afterburner is off, the exhaust nozzle closes to a smaller area of opening. Gas turbine engine bearings and seals. The main bearings have the critical function of supporting the main engine rotor. The number of bearings necessary for proper engine support is, for the most part, determined by the length and weight of the engine rotor. The length and weight are directly affected by the type of compressor used in the engine. Naturally, a two-spool compressor requires more bearing support. The minimum number of bearings required to support one shaft is one deep groove ball bearing, thrust and radial loads, and one straight roller bearing, radial load only. Sometimes, it is necessary to use more than one roller bearing, if the shaft is subject to vibration, or its length is excessive. The gas turbine rotors are supported by ball and roller bearings, which are anti-friction bearings. Figure 1-75. Many newer engines use hydraulic bearings, in which the outside race is surrounded by a thin film of oil. This reduces vibrations transmitted to the engine. In general, anti-friction bearings are preferred largely because they offer little rotational resistance, facilitate precision alignment of rotating elements, are relatively inexpensive, are easily replaced, withstand high momentary overloads, are simple to cool, lubricate, and maintain, accommodate both radial and axial loads, and are relatively resistant to elevated temperatures. The main disadvantages are their vulnerability to foreign matter and tendency to fail without appreciable warning. Usually the ball bearings are positioned on the compressor or turbine shaft, so that they can absorb any axial, thrust, loads or radial loads. Because the roller bearings present a larger working surface, they are better equipped to support radial loads than thrust loads. Therefore, they are used primarily for this purpose. A typical ball or roller bearing assembly, 1-52. Cooling air 120 degrees F. Stainless steel shroud -350 degrees F. Fiberglass, aluminum foil, fiberglass silver foil, jet tailpipe 900 degrees F. Exhaust gas, 1000 degrees F. Figure 1-74. Insulation blanket with the temperatures obtained at the various locations shown. Includes a bearing support housing, which must be strongly constructed and supported in order to carry the radial and axial loads of the rapidly rotating rotor. The bearing housing usually contains oil seals to prevent the oil leaking from its normal path of flow. It also delivers the oil to the bearing for its lubrication, usually through spray nozzles. The oil seals may be the labyrinth or thread, helical type. These seals also may be pressurized to minimize oil leaking along the compressor shaft. The labyrinth seal is usually pressurized, but the helical seal depends solely on reverse threading to stop oil leakage. These two types of seals are very similar, differing only in thread size and the fact that the labyrinth seal is pressurized. Another type of oil seal used on some of the later engines is the carbon seal. These seals are usually spring-loaded and are similar in material and application to the carbon brushes used in electrical motors. Carbon seals rest against a surface, provided to create a sealed bearing cavity or void. Thus, the oil is prevented from leaking out along the shaft into the compressor airflow or the turbine section. Figure 1-76. The ball or roller bearing is fitted into the bearing housing, and may have a self-aligning feature. If a bearing is self-aligning, it is usually seated in a spherical ring. This allows the shaft a certain amount of radial movement without transmitting stress to the bearing inner race. The bearing surface is usually provided by a machined journal on the appropriate shaft. The bearing is usually locked in position by a steel snap ring or other suitable locking device. The rotor shaft also provides the matching surface for the oil seals in the bearing housing. These machined surfaces are called lands, and fit in rather close to the oil seal. 1-53. Ball bearing roller bearing. Preformed sleeve bearing slipper bearing. Figure 1-75. Types of main bearings used for gas turbine rotor support. Turboprop engines. The turbopropeller, turboprop, engine is a combination of a gas turbine engine, reduction gearbox, and a propeller. Figure 1-77. Turboprops are basically gas turbine engines that have a compressor, combustion chambers, turbine, and an exhaust nozzle, gas generator, all of which operate in the same manner as any other gas engine. However, the difference is that the turbine in the turboprop engine usually has extra stages to extract energy to drive the propeller. In addition to operating the compressor and accessories, the turboprop turbine transmits increased power forward through a shaft and a gear train to drive the propeller. The increased power is generated by the exhaust gases passing through additional stages of the turbine. Some engines use a multi-rotor turbine with coaxial shafts for independent driving of the compressor and propeller. Although there are 3 turbines utilized in this illustration, as many as 5 turbine stages have been used for driving the 2 rotor elements, propeller, and accessories. The exhaust gases also contribute to engine power output through thrust production. Although the amount of energy available for thrust is considerably reduced, 2 basic types of turboprop engine are in use, fixed turbine and free turbine. The fixed turbine has a mechanical connection from the gas generator, gas turbine engine, to the reduction gearbox, spacers seal housing, bearing inner race seals, figure 1-76, carbon oil seal, and propeller. The free turbine has only an air link from gas generator to the power turbines. There is no mechanical link from the propeller to the gas turbine engine, gas generator. 1-54. Figure 1-77. PT6 turboprop engine. There are advantages and disadvantages of each system, with the airframe generally dictating the system used. Since the basic components of normal gas turbine and turboprop engines differ slightly only in design features, it should be fairly simple to apply acquired knowledge of the basic gas turbine to the turboprop. The typical turboprop engine can be broken down into assemblies as follows. 1. The power section assembly contains the usual major components of a gas turbine engine, that is, compressor, combustion chamber, turbine, and exhaust sections. 2. The reduction gear or gearbox assembly contains those sections unique to turboprop configurations. 3. The torque meter assembly transmits the torque from the engine to the gearbox of the reduction section. 4. The accessory drive housing assembly, mounted on the bottom of the compressor air inlet housing. It includes the necessary gear trains for driving all power section-driven accessories at their proper RPM in relation to engine RPM. Turboshaft engines. A gas turbine engine that delivers power through a shaft to operate something other than a propeller is referred to as a turboshaft engine. Figure 1-78. The output shaft may be coupled directly to the engine turbine, or the shaft may be driven by a turbine of its own. Free turbine. Located in the exhaust stream. As mentioned with the turboprop, the free turbine rotates independently. This principle is used extensively in current production of turboshaft engines. The turboshaft engine's output is measured in horsepower instead of thrust, because the power output is a turning shaft. Turbofan engines. The turbofan gas turbine engine is, in principle, the same as a turboprop, except that the propeller is replaced by a duct-enclosed axial flow fan. Figure 1-79. The fan can be a part of the first stage compressor blades, or can be mounted as a separate set of fan blades. The blades can be mounted forward of the compressor. The general principle of the fan engine is to convert more of the fuel energy into pressure. With more of the energy converted to pressure, a greater product of pressure times area can be achieved. One of the major advantages is turbofan production of this additional thrust without increasing fuel flow. The end result is fuel economy with the consequent increase in range, because more of the fuel energy is turned into pressure in the turbofan engine. Additional stages must be added in the turbine section to provide the power to drive the fan. This means there is less energy left over and less thrust from the core exhaust gases. Also, in a mixed exhaust nozzle, where fan air and core air mix in a common nozzle before entering ambient conditions, the exhaust nozzle must be larger in area. The result is that the fan develops most of the thrust. The thrust produced by the fan more than makes up for the decrease in thrust of the core gas generator of the engine. Depending on the fan design and bypass ratio, it produces 80% of the turbofan engine's total thrust. 1-55. Figure 1-78. Turboshaft engine. Figure 1-79. Turbofan engine. 1-56. Two different exhaust nozzle designs are used with turbofan engines. The air leaving the fan can be ducted overboard by a separate fan nozzle. Figure 1-43, or it can be ducted along the outer case of the basic engine to be discharged through the mixed nozzle. Core and fan exhaust together. The fan air is either mixed with the exhaust gases before it is discharged, mixed or common nozzle, or it passes directly to the atmosphere without prior mixing, separate nozzle. Turbofans are the most widely used gas turbine engine for air transport aircraft. The turbofan is a compromise between the good operating efficiency and high thrust capability of a turboprop and the high speed, high altitude capability of a turbojet. Turbine engine operating principles. The principle used by a gas turbine engine as it provides force to move an airplane is based on Newton's law of momentum. This law states that for every action there is an equal and opposite reaction. Therefore, if the engine accelerates a mass of air, action, it applies a force on the aircraft, reaction. The turbofan generates thrust by giving a relatively slower acceleration to a large quantity of air. The old pure turbojet engine achieves thrust by imparting greater acceleration to a smaller quantity of air. This was its main problem with fuel consumption and noise. The mass of air is accelerated within the engine by the use of a continuous flow cycle. Ambient air enters the inlet diffuser where it is subjected to changes in temperature, pressure, and velocity due to ram effect. The compressor then increases pressure and temperature of the air mechanically. The air continues at constant pressure to the burner section, where its temperature is increased by combustion of fuel. The energy is taken from the hot gas by expanding through a turbine which drives the compressor, and by expanding through an exhaust nozzle designed to discharge the exhaust gas at high velocity to produce thrust. The high-velocity gases from the engine may be considered continuous, imparting this force against the aircraft in which it is installed, thereby producing thrust. The formula for thrust can be derived from Newton's second law, which states that force is proportional to the product of mass and acceleration. This law is expressed in the formula, F equals m times a, where F equals force in pounds, m equals mass in pounds per seconds, a equals acceleration in feet per seconds. In the above formula, mass is similar to weight, but it is actually a different quantity. Mass refers to the quantity of matter, while weight refers to the pull of gravity on that quantity of matter. At sea level under standard conditions, 1 pound of mass has a weight of 1 pound. To calculate the acceleration of a given mass, the gravitational constant is used as a unit of comparison. The force of gravity is 32.2 feet per second squared, foot/seconds 2. This means that a free-falling 1-pound object accelerates at the rate of 32.2 feet per second each second that gravity acts on it. Since the object mass weighs 1 pound, which is also the actual force imparted to it by gravity, it can be assumed that a force of 1 pound accelerates a 1-1 object at the rate of 32.2 foot/seconds 2. Also, a force of 10 pound accelerates a mass of 10 pound at the rate of 32.2 foot/seconds 2. This is assuming there is no friction or other resistance to overcome. It is now apparent that the ratio of the force in pounds is to the mass in pounds, as the acceleration in foot/seconds 2 is to 32.2. Using m to represent the mass in pounds, the formula may be expressed thus: F equals, or F equals ma mgg, where F equals force, m equals mass, a equals acceleration, g equals gravity. In any formula involving work, the time factor must be considered. It is convenient to have all time factors in equivalent units, that is, seconds, minutes, or hours. In calculating jet thrust, the term pounds of air per second is convenient, since the second is the same unit of time used for the force of gravity, thrust. Using the formula below, compute the force necessary to accelerate a mass of 50 pounds by 100 foot/seconds 2. F equals mag 50 pounds times 100 foot/seconds 2. F equals 32.2 foot/seconds 2. 5,000 pounds foot/seconds 2. F equals 32.2 foot/seconds 2. F equals 155 pounds. This illustrates that if the velocity mass per second is increased by 100, the resulting thrust is 155 pounds. 1-57. F equals Fn equals. Since the turbojet engine accelerates air, the following formula can be used to determine jet thrust, miss, V2-V1, G, where F equals force in pounds, miss equals mass flow in pounds divided by seconds, V1 equals inlet velocity, V2 equals jet velocity, exhaust, V2 minus V1 equals change in velocity, difference between inlet velocity and jet velocity, G equals acceleration of gravity, or 32.2 foot/seconds 2. As an example, to use the formula for changing the velocity of 100 pounds of mass airflow per second from 600 foot/seconds to 800 foot/seconds, the formula can be applied as follows: 100 pounds/seconds, 800 foot/seconds minus 600 foot/seconds, 32.2 foot/seconds 2. 20,000 pounds/seconds, 32.2 foot/seconds 2. F equals 621 pounds. As shown by the formula, if the mass airflow per second and the difference in the velocity of the air from the intake to the exhaust are known, it is easy to compute the force necessary to produce the change in the velocity. Therefore, the thrust of the engine must be equal to the force required to accelerate the air mass through the engine. Then, by using the symbol Fn for thrust pounds, the formula becomes miss V2-V1 G. Thrust of a gas turbine engine can be increased by two methods: increasing the mass flow of air through the engine, or increasing the gas velocity. If the velocity of the turbojet engine remains constant with respect to the aircraft, the thrust decreases if the speed of the aircraft is increased. This is because V1 increases in value. This does not present a serious problem. However, because as the aircraft speed increases, more air enters the engine, and jet velocity increases, the resultant net thrust is almost constant with increased airspeed. The Brayton cycle is the name given to the thermodynamic cycle of a gas turbine engine to produce thrust. This is a variable volume constant pressure cycle of events, and is commonly called the constant pressure cycle. A more recent term is continuous combustion cycle. The four continuous and constant events are intake, compression, expansion, includes power, and exhaust. These cycles are discussed as they apply to a gas turbine engine. In the intake cycle, air enters at ambient pressure and a constant volume. It leaves the intake at an increased pressure and a decrease in volume. At the compressor section, air is received from the intake at an increased pressure, slightly above ambient, and a slight decrease in volume. Air enters the compressor where it is compressed. It leaves the compressor with a large increase in pressure and decrease in volume, created by the mechanical action of the compressor. The next step, expansion, takes place in the combustion chamber by burning fuel, which expands the air by heating it. The pressure remains relatively constant, but a marked increase in volume takes place. The expanding gases move rearward through the turbine assembly and are converted from velocity energy to mechanical energy by the turbine. The exhaust section, which is a convergent duct, converts the expanding volume and decreasing pressure of the gases to a final high velocity. The force created inside the engine to keep this cycle continuous has an equal and opposite reaction, thrust, to move the aircraft forward. Bernoulli's principle. Whenever a stream of any fluid has its velocity increased at a given point, the pressure of the stream at that point is less than the rest of the stream, is applied to gas turbine engines through the design of convergent and divergent air ducts. The convergent duct increases velocity and decreases pressure. The divergent duct decreases velocity and increases pressure. The convergent principle is usually used for the exhaust nozzle. The divergent principle is used in the compressor and diffuser, where the air is slowing and pressurizing. Gas turbine engine performance. Thermal efficiency is a prime factor in gas turbine performance. It is the ratio of net work produced by the engine to the chemical energy supplied in the form of fuel. The three most important factors affecting the thermal efficiency are turbine inlet temperature, compression ratio, and the component efficiencies of the compressor and turbine. Other factors that affect thermal efficiency are compressor inlet temperature and combustion efficiency. Figure 1-80 shows the effect that changing compression ratio, compressor pressure ratio, has on thermal efficiency, when compressor inlet temperature and the component efficiencies of the compressor and turbine remain constant. The effects that compressor and turbine component efficiencies have on thermal efficiency when turbine and compressor inlet temperatures remain constant are shown in Figure 1-81. In actual operation, the turbine engine exhaust temperature varies directly with turbine inlet temperature at a constant compression ratio. 1-58. Thermal efficiency, in percent, 30, 25, 20, 15, 10, 5. Temperature, 1000 degrees Fahrenheit 1200 degrees Fahrenheit. 1400 degrees Fahrenheit 1600 degrees Fahrenheit. Turbine inlet temperature increase, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. Compression ratio, Figure 1-80. The effect of compression ratio on thermal efficiency. 0.100200300 400,500. Turbine bucket life, in hours. Figure 1-82. Effect of turbine inlet temperature on turbine bucket life. 30. Thermal efficiency, in percent. Efficiency of C&T 90%, 80%, 85%, 75%. 25, 20, 15, 10, 5, 0, 0, 1, 2, 3, 4, 5, 6, 7, 8. Compression ratio, Figure 1-81. Turbine and compressor efficiency versus thermal efficiency. RPM is a direct measure of compression ratio, therefore, at constant RPM, maximum thermal efficiency can be obtained by maintaining the highest possible exhaust temperature. Since engine life is greatly reduced at high turbine inlet temperatures, the operator should not exceed the exhaust temperatures specified for continuous operation. Figure 1-82 illustrates the effect of turbine inlet temperature on turbine blade life. In the previous discussion, it was assumed that the state of the air at the inlet to the compressor remains constant. Since this is a practical application of a turbine engine, it becomes necessary to analyze the effect of varying inlet conditions on the thrust or power produced. The three principal variables that affect inlet conditions are the speed of the aircraft, the altitude of the aircraft, and the ambient temperature. To make the analysis simpler, the combination of these three variables can be represented by a single variable called stagnation density. The power produced by a turbine engine is proportional to the stagnation density at the inlet. The next three illustrations show how changing the density by varying altitude, airspeed, and outside air temperature affects the power level of the engine. Figure 1-83 shows that the thrust output improves rapidly with a reduction in outside air temperature, OAT, at constant altitude, RPM, and airspeed. This increase occurs partly because the energy required per pound of airflow to drive the compressor varies directly with the temperature, leaving more energy to develop thrust. In addition, the thrust output increases since the air at reduced temperature has an increased density. The increase in density causes the mass flow through the engine to increase. The altitude effect on thrust, as shown in Figure 1-84, can also be discussed as a density and temperature effect. In this case, an increase in altitude causes a decrease in pressure and temperature. Constant altitude, RPM, and airspeed, net thrust, 100%, 60%, Deck STD Inc., outside air temperature, OAT. Figure 1-83, effective OAT on thrust output, 1-59. 100, constant RPM, altitude, and OAT. 100, constant airspeed and RPM, thrust, percent sea level rated, 50, 0, 0, 10, 20, 30, 40, 50, altitude, 1000 of foot. Figure 1-84. Effective altitude on thrust output. Since the temperature lapse rate is lower than the pressure lapse rate as altitude is increased, the density is decreased. Although the decreased temperature increases thrust, the effect of decreased density more than offsets the effect of the colder temperature. The net result of increased altitude is a reduction in the thrust output. The effect of airspeed on the thrust of a gas turbine engine is shown in Figure 1-85. To explain the airspeed effect, it is necessary to understand first the effect of airspeed on the factors that combine to produce net thrust, specific thrust and engine airflow. Specific thrust is the net thrust in pounds developed per pound of airflow per second. It is the remainder of specific gross thrust minus specific ram drag. As airspeed is increased, ram drag increases rapidly. The exhaust velocity remains relatively constant. Thus, the effect of the increase in airspeed results in decreased specific thrust. Figure 1-85. In the low speed range, the specific thrust decreases faster than the airflow increases, and causes a decrease in net thrust. As the airspeed increases into the higher range, the airflow increases faster than the specific thrust decreases and causes the net thrust to increase until sonic velocity is reached. The effect of the combination on net thrust is illustrated in Figure 1-86. Constant RPM, altitude, and OAT, airflow, in pounds/seconds, total airflow, W. Specific thrust. 0. Increase. Ts. Figure 1-86. Effect of airspeed on specific thrust and total engine airflow. Ram recovery. A rise in pressure above existing outside atmospheric pressure at the engine inlet, as a result of the forward velocity of an aircraft, is referred to as ram pressure. Since any ram effect causes an increase in compressor entrance pressure over atmospheric, the resulting pressure rise causes an increase in the mass airflow and gas velocity, both of which tend to increase thrust. Although ram effect increases engine thrust, the thrust being produced by the engine decreases for a given throttle setting as the aircraft gains airspeed. Therefore, two opposing trends occur when an aircraft speed is increased. What actually takes place is the net result of these two different effects. An engine's thrust output temporarily decreases as aircraft speed increases from static, but soon ceases to decrease, moving toward higher speeds. Thrust output begins to increase again due to the increased pressure of ram recovery. Net thrust, 50, with ram. Without ram, 0, 0, ts. Figure 1-85. Effect of airspeed on net thrust, 1-60, increase. Chapter 2. Engine fuel and fuel metering system.